within the data. However, there are some issues when you want to apply deep learning methods to solve anomaly detection. Usually, for deep learning methods to work well, it requires a large-scale label data to achieve good performances. But in the setting of anomaly detection, you usually don't have a lot of data that is labeled anomaly. Maybe because it's expensive to detect one, or maybe it's very rare. So it's not as popular as nominal data. For example, like for transactions, most of the time you trust that people are conducting valid transactions. There are only few of them are actually anomaly. So this paper proposed a solution to this issue by leveraging a limited number of label anomalies as a prior knowledge. So these label anomalies may come from, let's say, a deployed anomaly detection system, and then the purpose is that you want to improve it further, or it from manual checking. Like there are actually people who are labeling that this data point is anomaly. So previous deep learning methods for anomaly detection usually adopt peptide approach. They first have a representation learning model to derive the feature representation of the data. For example, they can use autoencoder or GAN. And then after they receive the feature embedding, the later process that we use an anomaly measuring model to derive the anomaly score. So the drawback of this approach is that the representation learning process and the anomaly detection method are separated. So that could lead to the problem that the learn embedding feature might be suboptimal for the anomaly detection task. So some of the current deep learning methods for anomaly detection, they also joined these two tasks together. However, there's still there the optimization for the representation learning step, which might lead to still suboptimal representation of the anomaly detection task. Whereas this paper adopt end-to-end approach, they basically directly go from the input feature vectors, and then they build a model that can derive the anomaly score. And then this process is end-to-end, meaning that all the model parameters in between can be learned and optimized so that the anomaly score is well suited for detecting anomalies in the future. So the setting of the problem is as following. In the input, you have a mixture of unlabeled data and anomaly data. So you have endpoints is labeled is unlabeled data. Data means that it could be normal or anomaly. We don't know that. So this will come more clear in the experiments when they try different level of anomaly in the unlabeled data. And then there is a K points in which you know for sure that they are anomalies. The objective is that you will learn anomaly scoring function so that the score of the anomaly will be higher than the score of nominal data points. So is there any questions so far about the problem setting, the input and the objective? Okay, if there's no question, I will move on to the next slide. So this picture is the overall framework of the model presented in the paper, which we call Deviation Network. So there are three components to this framework. The first component is multi-layer neural net that can generate for every data instances. So if you look at the picture, you can say that given the input X, the output of this component is a score. Then that score is going to be defined as anomaly score. The second component is they call a reference score generation. So the function of this component is that it's going to generate a mean score of nominal data points. The mean score of nominal data points, like of the normal data points. So for the loss function, the third component, the goal they want to achieve with this loss function is that the score of anomaly data points should be significantly deviate away from the mean score of the nominal data points, which is the mean value here. And on the other hand, the scores of the normal data points should be as close as possible to this mean value. So any question about this architecture?
So I have a question. So the nominal data points, can they take the anomaly data, or is it only the unlabeled data?
So the nominal data point comes from the mixture, the unlabeled data, the set of unlabeled data.
Right.
Yeah. So your question is that?
Yeah, so I was just checking if they mix in the anomaly data as well. So they just pick from the unlabeled data, right?
Yeah, they just pick from the unlabeled data.
Okay.
So that in the paper they mentioned there are two ways that you can generate this reference score. You can generate from the set of unlabeled data, or you can generate it from a prior distribution that you define by yourself. So in this particular paper, they choose Gaussian normal distribution as a prior distribution for this reference score generation. Okay, so let's go into details of this architecture. So on the left, you see that there is the input layer, which you have value of X, and then you go through some kind of encoder, some kind of neural net to produce intermediate representation. And then given this intermediate representation Q, the score is defined as the linear regression values, basically the inner product between the model parameter theta S and the intermediate representation Q. So as I mentioned in the previous line, in this paper, choose Gaussian normal distribution as a prior distribution for generating the reference score. So the way they do it is that they're gonna randomly generate sample L points from this normal distribution, and they just simply calculate the mean of these points to derive the value of mu and the value of sigma. Any question about this? Okay, so now we have the score for every data point, and we have the reference score for the nominal data points. So this, if you remember that the loss function, what we want to achieve with this loss function is that the score of anomaly is significantly different from the mean score mu. And the score of nominal data point should be as close as possible to this mu value. So let's look at the loss. So first of all, they're gonna define a deviation value for every data point x, which is def x here. It's basically the normalization, the z value, the score value of the anomaly score minus mu value and divided by the sigma, the standard deviation. And then for each data point, the loss is defined as following. So y is a label of the data point. It is 1 if anomaly and 0 otherwise. So this loss function is similar to conjunctive loss. Basically, it's gonna minimize. Yes, let's look at the loss value. If x is an anomaly, right, then 1 minus y will be 0. Then basically what you want to minimize is this second term, max of 0 and a minus def of x. So if you look at the value, if we want to minimize loss when x is an anomaly, then what you want to achieve is that the deviation value of the anomaly should be as close to this threshold a as possible. And when x is a nominal data point, then you want the the deviation value to be close to 0 as possible. Does it make sense? Okay, great. So, so imagine that after the optimization process, they're gonna derive the representation of the anomaly so that the deviation score of the anomaly will be close to a very high positive value, and the deviation score of the normal data points could be around 0. So let's look at the algorithm, right? So as I highlighted here, for each iteration, for each batch, this algorithm, they use a mini batch optimization approach. So for each batch, they're gonna random for data points from both the unlabeled data and the anomaly data points. And then there's sample from the Gaussian distribution to compute the mu and the sigma. And then after that, they derive the loss and then performs gradient descent to learn the parameters. So any question about the framework, about the algorithm before I move to the experiments? Okay. So let's go to the experiments part. So this paper performed several experiments with 9 different data sets. So some of them are a real world data sets with anomalies in it. The fraud one comes from the finance domain. Backdoor is about backdoor attack in cybersecurity. And URLs consist of some malicious URLs. Thyroid is some kind of disease. So for the rest, they are dataset with semantic anomalies, meaning that there are some data points which they are not semantically similar to the rest of the dataset. So the first column is the number of objects, a number of data points in this in each dataset. The second column is the dimensionality of the data points. This column, the F1, is a percentage of anomalies in the training. So when they split the data points for training and testing, they manage to guarantee the percentage of the anomalies in the training is at this value, and the F2 is percentage of the total anomalies in the data set. About the baseline, this paper considers 4 different baselines. So repent is a deep anomaly detection with limited label data. So in some sense, it's similar to the setting of this paper, which also consider a limited label of anomaly. The SVDD is feature learning for anomaly detection. Okay, so FSNet is a field classification. The 2 metrics that the paper consider is IUC ROC and IUC precision recall. So let's look at the comparison. So the first insight is that the proposed framework outperforms baseline for both metrics. How the level of improvement is presented in percentage in the slide. So you can see that it's improved substantially by slides. The insight number 2 is that the proposed framework is more data efficient, in the sense that when they vary the amount of anomalies in the data set, in the training data, then you see that net is still perform very well across the data set, which means that it requires less label data to achieve the same level of performance as compared to baselines. The third insight is they try to see whether the proposed framework is robust to the contamination. So contamination means that they're gonna vary the percentage of anomaly in the unlabeled data. You have a high level of contamination mean that you have more anomaly in the unlabeled data, which may affect the performance of the model. So again, the horizontal line is a contamination level, and the vertical line is performance. You can still see that DevNet is substantially better than the baseline. So for different components of DevNet, they perform here some comparison. So for the first column here, Dev is actually default framework architectures. Ref is DevNet without this anomaly score layer. And linear is the one that you don't use nonlinear transformation, just a linear layer. And 3HL is DevNet with 3 hidden layers instead of just one as in the default architecture. So you can see that the anomaly score layer actually have some have contribution to the overall performances, as well as the nonlinear structure also helpful to contribute to the performance of DevNet. Last one is a scalability test. So in this experiment, they synthesize 4 different datasets with varying size and dimensionalities. So look at this picture. You can see that DevNet scaled linearly with the size of the data as well as the dimensionality of the data. And it's not the worst among the considered models. Okay, so in conclusion, this paper deal with the problem of anomaly detection with limited label data. It proposed an end-to-end framework for learning anomaly scores. It offers several advantages like substantial improvement over the baseline. It is more data efficient, it's more robust to contamination, and it's scale linearly with the data size and dimensionality. So with that, I could finish my presentation here. And if you have any question, please raise your hand.